Hi there, we're getting closer to the exam, and today I would like to go through calculations with electrode potential, some of the key concepts, and I will give you some tips on how to not rely on your memory, but really try to work out the logic and to work out answers to questions just by using your full understanding rather than trying to memorize. Relative to this topic, like reduction, oxidation, reducing, oxidizing agent, and so on, because I know during the exam we could have these like blackouts where it's really really hard to remember the things that we sometimes just think we know blind. Yeah, so I would like to show you the logic that I use in this topic. Okay, so I've taken this question from AQA 2017 just because it has all the nicest step for this topic because the first thing to be confident with is the oxidation state. There are other videos about redox equations, so I will put a little card on the top if you want to check this out. Then we'll look at oxidizing reducing agent, the conventional representation of the cell, and then a calculation with the electric potential. Okay, so in terms of oxidation state, this is a common question, worth it to be able to do it also for transition metal topic, because you need to be able to find the oxidation state. In this case, is of nitrogen, okay, which means that oxygen will be in its standard oxidation state, which is -2. So when there is an excess charge, you can do it either just in your mind or you can set up a little equation, knowing that each oxygen, I'm going to write it up here, so each oxygen contributes it or has an oxidation number of -2. But there are three of them, so the total charge that it contributes is -6. So we have our X -6 must be equal to -1 because X is the oxidation number of nitrogen, which means that this nitrogen must be +1 to keep that excess minus charge. Well, here it's a lot more straightforward because oxygen is -2 and it's a neutral ionic compound, sorry, the neutral covalent compound, so nitrogen would be +2. So relatively straightforward here. Weakest reducing agent. So the electric potential, I see it as a measure of the amount of electrons that flow in a system. In theory, and sometimes you have questions where you're asked to explain it in terms of equilibriums. In fact, very often you have this actually always as a equilibrium, okay? Because we can say this in different ways. So how I say that for me is really, really simple to think about it. A bit counterintuitive in terms of electrons, because I know electrons are negative, but if the voltage is a measure of the electrons that flow to a system, right? The more positive it is, the more likely the electrons are to flow to that system. Okay, as if that makes sense to you. The more positive, more electrons to it. While negative electrons would go away because it's voltage, a measurement of the flow of electrons. Not really, so let's not get into the physics of it, but it's just for me the easy way to remember it. So that I know that the most positive it is, the more likely is to have the electron towards itself. So the other way to think about it is that the more positive the voltage, the more the equilibrium will lie. So if this was written as an equilibrium, it will lie on the left hand side. Okay, which means that it's more likely to be reduced. Okay, so if it's more likely to be reduced, what type of agent would that be? It would be an oxidizing agent. Okay, so I would like you to stop there for a moment and think about how do you know which one is the weakest or the strongest reducing agent? What's your logic method? Don't use your memory. Well, how do you get there with logic? Mine is like like that, visualizing that, oh, if it's positive, more voltage, electrons towards it. So if I think about that, then I can articulate it if I have to answer in terms of equilibrium or like a little bit of logic, like in this question. Okay, so clearing up a little bit the screen. I was saying weakest reducing agent. There is a tip here that you can think about. Okay, this strongest. So if we always look on the right hand side, we can find the strongest oxidizing agent, right? Because all of these equations are in terms of reduction potential. So if all of these are reduced, so we know it's reduction, then we can all compare them in terms of oxidizing agent, because all of these that are reduced, we can consider, okay, they're oxidizing agents. So the strongest one would be oxidizing agent itself reduced, gets more electron toward itself, the most positive. So always the most positive B, it would be the strongest reducing agent. The strongest reducing agent will contain the weakest oxidizing agent. Okay, take that in for a moment. Because if you think about it, could it be chlorine, the reducing agent? No, because that doesn't get oxidized, doesn't lose even more electrons. But what about the chloride ion? Yeah, technically this could lose electrons. Okay, this could lose electrons and become Cl2. So this could be considered a reducing agent. Oh, reducing agent because it's oxidized. Okay, because remember, we're looking at the equation we look at this equation in both directions. Okay, so how does oh, okay. So the weakest reducing agent would be chloride minus, because yeah, even though we can look at, of course, on the right and on the opposite side, because itself will lose electrons. So basically all on this side could be considered oxidizing agents, right? Because they will lose electron. Look at the directions of the electrons are on the opposite side. But the weakest one will be Cl minus, because it's more positive, so more likely that the electrons would go towards it rather than away from this cell. Okay, so the weakest reducing agent would be the chloride minus. So I hope that made sense. So the tip is the most positive is the strongest oxidizing agent, which will contain the weakest reducing agent. Okay, let's go to the next part. So the conventional representation of the cell that has an EMF of 0.43. So here there is a bit to work out. Okay, it's a bit tricky, this question. So first of all, how do you work out the EMF? So the way I think about it is that this is always given as a reduction potential. As you can see, all of the reactions here are reduced. Okay, so one reaction will have to be oxidized. The one that is oxidized would be the one that changes sign. That's why you will always have the reduction, so the electric potential of the equation reduced minus the one that is oxidized. Why? Well, because the oxide you have to flip it. That's why you change the sign of that. But here takes a little bit of work out to think about what would be 0.43. Yeah, and putting numbers together, I only see that the right ones could be these two. Okay, because 0.77, it's this ion is the most positive, the most likely to gain electrons, so the other one will be reduced. Let me clear up 1 second the screen so I have a little bit more space to draw it out. Okay, so so as I was saying, those two would be the one that if you have one positive and the other one is negative, it would give you for 0.43. So how I know that this will flip? Well, because first of all, the most positive, remember, is the one that is going to be reduced electron towards it. So the other one will be oxidized. So the reaction will be different, right? Like you would have to swap this round. Okay, like this. So for ion would stay as a 3 plus, as gaining one electron to form, and this is a mistake by the way, should be 2 plus. Wow, that's a past paper with a little mistake in it. Anyway, we found that. It begins an electron, becomes 2 plus, and then we have the copper, and that's the one that we need to flip around because it's less positive, yeah, than iron, so it is going to be oxidized, and this is what it looks like, 2 plus and 2 E minus. So it would be 0.77 minus 0.34, giving us plus 0.43. So here, introduction to the calculation, and seeing this should come to you and thinking always that you have one reduction and one oxidation. Okay, the oxidized one will be the least positive because it's the less is weaker, um, is a weaker oxidizing agent, reducing agent. So would be is the most likely to be oxidized. Okay, so the conventional representation, that's what I wanted to get. Anyway, this question is a bit weird, but I wanted to get to the conventional representation. So the conventional representation is the one that has the lines. Okay, so you have something line, something salt bridge, something the other line. Okay, so I have a way to remember it. Okay, you always start. So these lines means in contact with. Okay, which means that you will have something in contact with the electrode, in contact with the salt bridge that is in contact with the other solution. So we will have the copper electrode is in contact with the copper solution, which is in contact with the salt bridge, in contact with what? With the other solution, which would be ion 3 plus, comma ion 2 plus, which is in contact with what? Platinum electrode. Okay, because this is a solution. This is a half cell that it's a solution, so we cannot have the solid electrode, but instead we have platinum. Okay, so I hope that is in contact with makes sense and you can visualize it. So the next question would be use the data from table 4 to identify an acid that will oxidize copper. Explain your choice of acid. Okay, so first of all, you need to find the acids that are in this equation. In this set of electrode half equations, and of course the acid will be the one that donate protons. So we have 1, we have 2, we have just the hydrogen, and that's it. Those are the ones. So we need to oxidize copper. So what is copper? Is our reducing agent. Okay, so copper would be our reducing agent. Oh, why is doing that? Agent. So if that's our reducing agent, you need to think about the electrode potential that would be more positive than copper because that has to be oxidized. Oxidizing agent has to be reduced. So basically, think about we want an acid that is reduced. So if it's reduced, it would have a more positive electron potential. So I would like you to always keep in mind that more positive electron towards it. And then you can work it out all the rest. Okay, so looking up copper, what the most positive one will be NO3 minus. And guess what acid that is nitric acid. So HNO3 will be the acid that is able to oxidize copper. Okay, so possible equation for the reaction. So you need to put the equations together, and I would suggest you to write them in the correct order. So we have the nitric acid written as a half equation like this. You know that this stays in this direction because it's oxidized. It's reduced because it's the most positive potential, and the copper one will be oxidized, so will be exactly the opposite. Also remember oxidation, loss of electrons, so the electrons they have to go on the right hand side as a product. Now you need to think about how do they come together, these two equations. So you need to balance them by cancelling out electrons. And so we have 3 at the top, 2 at the bottom. So we need to multiply the whole equations by their balancing numbers so that you have the same number of electrons and they cancel out. So we time this by 2 and this by 3. So that you get to the full balanced equation, you would have a 3 copper plus 2 NO3 minus plus 8 H plus. Electrons have cancelled out. They all form the balancing keeps for the products too. 2 NO plus 4 H2Os plus, I'm going to go down here, 3 Cu 2 plus. This is your balanced equation. Can you find the EMF? Yes, because we know that the one that stays the same is the one reduced. Remember that the balancing doesn't change the balancing. Okay, not like enthalpy calculations. And the copper is the one that will change sign because it is the least positive, the one oxidized. Okay, so this will give us 0.62 volts. and this is your solution. So I hope it makes sense, and I hope this logic of understanding what's positive or negative will help you understand or do this type of workout, like weakest reducing oxidizing agent. Okay, so I hope that it's helpful. If not, drop a comment and I'm happy to answer and support you to the exams. Thank you, and I'll see you in the next video.